with I equals 0, and you will discover what that means.
Yes, thank you for the invitation and the introduction. It's really nice to be back in Antwerp and here, where I did indeed my PhD after long time. And seeing people again and meeting new people is really nice. Yes, I will talk about classification of quadratic pairs over fields with IT equals 0, and this is joint work with Anne Quéguiner-Mathieu. So fields with IT equals 0, this property I will soon define. But the main object of the talk actually are quadratic pairs, but I will they will appear really towards the end of the talk, just because I decided to avoid the technicality as much as I can. That's why, indeed, in my base field, I put this assumption of the characteristic. I assume that the characteristic is not true. In this context, quadratic pairs and orthogonal involution, which I will define soon, orthogonal involution, they are the same object. So the main part of the talk, where I will provide the result, I will provide it in terms of orthogonal involution. And but yes, so I will define the main thing really in the end. But let me just say that quadratic pairs can be considered as a twisted form of quadratic forms, and hence many classical results that we know about quadratic forms are tried to extend it to quadratic in this context. And today I will be referring one of these problems, namely the classification problems. And for this purpose I will start with a very introductory section referring the classification result for quadratic forms. Yes. So let's take a finite dimensional vector space over F, a quadratic form M of V over F is a map that satisfies the following two conditions. So Q lambda V, that is lambda square V, lambda in the base here in the vector space. And then you can define a map using this quadratic form as follows. Q V minus Q V. And we ask this map to be bilinear. Bilinear map. That's linear input factor, and it's easily can be seen that it is symmetric. Q, is it too small?
Yes.
Okay, I will try to write it more bigger. Q VW minus QV minus QW. Yes. And in the talk, quadratic forms that appear, they will be non-degenerate. So let me call. Q is non-degenerate. If the only vector that satisfies this condition, okay, I give a name to this bilinear map, EQ, is 0 for V, V is the 0 vector. The only vector satisfying this condition is the 0 vector. In that case, we call it non-degenerate. So, and classification problem is basically we want to determine the isomorphism classes. And for quadratic form, will be isometry classes of quadratic forms. So, we call an isometry. So, if Q1, Q2 are two quadratic forms over F, we call Q1 they are isometric, and we do it like this. if you have a bijection F that's compatible with the quadratic forms. Q2, that is, you ask this diagonal for Witt such that it's mean Q2 as Q1
Too small.
Okay, yes. I will try. Yes, isometry. Okay, so we want to determine the isometry classes of this object, and for this purpose, there are some invariants, so-called classical invariants, that are attached to quadratic forms, and we expect them to help us to determine, to help us to deal the problem. Well, first of all, for example, if you have two quadratic forms, they are isometric. Of course, the dimension of the vector spaces has to be the same. So dimension is such an invariant. And I will just talk this classical invariant. So the other two invariant are namely discriminant and Clifford algebra. Let me define that too. So that's 4 over F. You define the Clifford algebra, you take the tensor algebra of V of your vector space and quotient by the ideal generated by such elements. Okay, we multiply C of Q. This is Clifford algebra of Q. And okay, it has a natural Z2 grading because you see tensor algebra, you take the tensor product of V with itself. So even the number of times and odd the number of times, if you consider, then it will give you a Z2 grading. So you have such a composition. And even degree. So this is it's called even Clifford algebra. Okay, this is the Clifford algebra of the Q, and I will define the discriminant through the even part. It is a yes semi-simple algebra over F, and the center is an étale quadratic F algebra. Quadratic F algebra.
If you assume that Q is even dimensional.
No, but I assume that non-degenerate.
No, but the center, if Q is odd dimensional, then the center is just F. This center of Caesar. So this is the last line is correct when Q is even dimensional.
Yes, okay, even dimensional. Yes, yes. Mm-hmm. Yes, yes, I wanted to give you the definition in once. So at quadratic F algebra, so it will be given as by a non-zero element, and the square plus of this D is the discriminant of your quadratic form. The square plus. Yes. So the Clifford algebra and the discriminant. Now I am only give the classification result. So yeah, over the fields, over these fields that we are interested, over fields with I3 equals 0, I will just give the statement that we have the classification result, but I need to define the I3 equals 0, the property I3 equals 0. Yes, for this I would need to recall quickly the Witt ring of the field. So the quadratic form let's say QB a quadratic form, is hyperbolic, is called hyperbolic if there exists a subspace of the half dimension such that the quadratic form is trivial on this subvector space. And with this, I can define some equivalents for two quadratic forms Q1 and Q2. Q2, we call they are equivalent, and yeah, this is the notation. If after adding some hyperbolic quadratic form, they become isometric. If there some hyperbolic quadratic form such that and the width string of the field F, so you consider the isometry class of quadratic forms over F and quotient by this equivalent relations. And okay, this is the ring. The operations are induced by the orthogonal sum and the tensor product, how you would expect them to be defined. And if you consider the isometry class, the classes of even dimensional quadratic forms, this is an ideal in your ring, and we multiply by F. So that third is just the third power of this this ideal. And this is such a. And today we are we are interested on fields with when the third power is trivial. Like some very simple example would be transcendence degree 2 extension over complex number, or transcendence degree 1 extension over finite field, or you can consider Lorentz series over complex number. Well, for the people who know about quadratic forms, will realize that these all fields have invariant form, in the sense they do not support too interesting quadratic forms. However, we do have some construction due to Merkuriev to construct fields with this property and carrying enough interesting quadratic forms. So we have interesting interesting examples with this property I3 equals 0. And yes, now I will give the classification result. This is due to Edman Lam. 4. So I3F is trivial if and only if quadratic forms over F are classified by isometry up to isometry by dimension, discriminant, and Clifford algebra. Yes, this is just an introduction section. This is a very well-known result, nice result, and I will try to explain. Yes, we try to extend this this result to orthogonal involution, quadratic pairs.
Yes.
Yes.
So by they are classified. Do we mean like they are isometric if they have the same dimension discriminant in the Clifford algebra?
Yes, I3 is equal to 0 if and only if when you have two quadratic forms, they are isometric.
If and only if they have the same three properties.
Yes.
Okay.
Yes.
Yeah, thank you.
Yes. And yes, this is something that we want to extend to these non-trivial objects that I will explain. And as I said, I work on characteristic NATO, so I will explain that in terms of orthogonal evolution. So let me now define orthogonal evolutions.
Can you make a suggestion?
Yes, I will make it, of course, I will try to make it more clear why we have this hope, when I will give example of evolution.
I think it would be good at this point to give to illustrate like the case where both fails. Like what is when I3 is not 0, what is a typical form that shows like that you cannot distinguish it from a trivial form. When I3 is not 0. I mean, okay, I can formulate what I want to hint at. Like, I mean, like the I3 condition is related to threefold Pfister forms.
Yes.
Being hyperbolic.
Yes.
And,
okay.
And this it's this thing that as soon as you have one such threefold, maybe you could elaborate briefly, like that would have trivial invariants. A threefold Pfister form would have trivial invariants.
Yes.
So you could not distinguish it from a hyperbolic threefold Pfister form if there is a non-hyperbolic one.
Yes,
So
like
if
we consider, for example, field. Okay, let's consider Q. Everybody is we can consider, for example, like quadratically. Yeah, okay, we can consider a field which is not quadratically closed, and then over such fields, for example, I can have the threefold Pfister form given x by x, y, and the non-square class. That would
take for example the form 8-dimensional form which has just one increase over Q.
Yeah. Okay,
let's take just a simple example to illustrate that that classification with these invariants will not always work.
Okay, the notation I'm not sure if is known, but yeah, this is just 8-dimensional quadratic form given by x1 square plus 2x8 square, and yeah, this kind of forms even dimensional. It has dimension 8 and it has trivial discriminant and Clifford invariant. We can compute, but it will be, for example, anisotropic if I consider over Q as suggested. And however, and hyperbolic forms, as I defined here, they do have trivial invariance. But if I consider over Q, this being anisotropic, it cannot be isometric to hyperbolic form over that field. Yes. Okay. Okay, orthogonal evolutions, they are defined on central simple algebras, so I will define first the later. A central simple F algebra is an algebra A over F, such that it is simple and the ring that is only exact ideals you have are trivial ones. The dimension as a vector space is finite, and the center, yeah, it's already appeared, but I think I didn't say the center. I mean the elements that commute with everything, basically. The center consists of F. We know that these algebras always have a square. Dimension is always a square of an integer. So in this case, dimension is square, and square is an integer. And this integer n, we call it a degree n. And I need another terminology as well. These algebras, we can always, it's very well known, we can always express as some matrix algebra over a division algebra for some division algebra D. The division algebra is unique up to isomorphism and some integer n, okay? And the index of the algebra is for the degree of this underlying division algebra. Okay, some example. Some examples. Really not good. Okay, n times n matrix algebra over the base field for an integer n. This is a central simple algebra. A trivial example for us. Let me give a non-trivial construction. Quaternion algebras. So for any non-zero element in your field, we can consider the four-dimensional vector space over F, which basis 1, I, J, and Ij, and define the following rule on the basis: I square equal to A, J square equal to B, and Ij equal to minus Ji. So this rule will give a ring structure on your vector space, and it turn it a central simple algebra. Dimension is 4, so the degree is 2. And a notation for this algebra, I will use this. I put AB in the ingredient that we use to construct the algebra in the parentheses. And I will not write, but it is also true that any central simple algebra of degree 2 can be described in this nice way. And then tensor product provides new examples. In particular, if you have a central simple algebra over F and a field extension, then extending scalar, that is a tensor K over F, this would be a central simple algebra over K. Okay. Now, I will define orthogonal involution. So let's A classical algebra over F, and involution on A is an anti-ring automorphism of order 2. And the restriction on that is identity. So here, starting from the first example, okay, during the talk, I think I won't be able to avoid the terminology. Whenever I have the matrix algebra over the base field, that I will refer split algebra. So this, whenever I say split algebra, you can consider this. And so let's define some evolution on these examples. Over matrix algebra over F, the transpose is an involution. Okay, before I wanted to also, I will not give the complete definition, but there are two types of such involution: orthogonal and symplectic. Basically, the set of symmetric element, that is the element x in your algebra A, such that sigma x is equal to x. This is a vector space, and the dimension of the vector space tells you whether the involution is orthogonal or symplectic. But let's not go too much in detail. But I have these two types, and yes, as I said, we are interested on orthogonal involution. So transpose is an orthogonal involution. Involution on and on the quaternion algebra, let's define the following map. So I am considering just quaternion algebra is enough, no need to representation. X define the map, the reduced norm of x minus x. So reduced norm, what's the reduced norm? Extending scalar, and by extending scalar, I can obtain a new algebra, and I can always find a field extension that's over this extension. My algebra becomes matrix algebra split, and I choose such a field extension, and in that case, x corresponds to a matrix, and the determinant of that matrix is the reduced norm of the element x. This, defining involution, this is a symplectic involution. Symplectic involution on Q, and actually it is the unique symplectic involution on the quaternion algebra. And we can define also the following. This is the inner automorphism given by I, and then composed with this symplectic involution. And this is an orthogonal involution. Involution on Q. Then here, if we consider sigma an involution on A, then sigma identity K is an involution on AK. And okay, notation for this, when I extend scalar, I will be denoting like this, and this one, sigma. Okay, so yeah, one last example also I will give to a little bit justify why we have this hope to expect that we can carry these classification results to orthogonal involution. So for a quadratic form, non-degenerate quadratic form. So using the bilinear form that we can match, I can define a map on the endomorphism ring. Okay, first of all, note that this is the set classical algebra. This is just the split algebra here. And Okay, it is how we define this is uniquely determined by the following rule. By Q, I could do that. Adjoining to the yes, so this you can define such a map, but this is an orthogonal involution. This is an orthogonal involution on endomorphism ring. So quadratic form, and then we obtain a orthogonal involution on the split algebra and the morphism ring. But actually, the converse also is true. Any orthogonal involution of this endomorphism ring can be obtained in this way by a quadratic form, which is unique up to a scalar factor from the base field n. So, and then, yes, as here I already mentioned, I can always find a field extension to split the algebra. So after some extension, my involution is just determined. It can be always as expressed by a quadratic form. This motivates our expectation to generalize the classification. And as in the quadratic form case, again, we define some invariants for involution that would correspond to the those classical invariants that I already defined in the split case. So now I will briefly define the analog of Clifford algebra and discriminant for orthogonal involutions. Discriminant. Okay. A sigma. Yeah, I just mean that A is a central algebra and this orthogonal involution. F algebra with orthogonal involution. Even okay, for the yes, before defining, let's just recall briefly the Clifford algebra quadratic form. As I said, it has a Z2 grading, so we have such a decomposition. So, and okay, we want to define invariants that in the split case would coincide with those invariants that exist. And then here the correspondence that I mentioned, it is the quadratic form there is determined uniquely up to a factor of from the base field. But we know that the Clifford algebra is not invariant after when we factor by some lambda here. The Clifford algebra change is not isomorphic. However, the even part is invariant. So what we do, we generalize the even Clifford algebra, and even Clifford algebra can be defined independently as follows: the tensor algebra of B tensor B, and then some relation you define. I will not write here, but you define some relation. And this is the idea behind of the definition of the Clifford algebra that I will now give. And to make it more precise, just let me remark also that V tensor V, you can identify this with the endomorphism ring of V. Basically, this is, yeah, I think very well known. I do as well, possibly. By this map, you can identify with the endomorphism ring. So basically, what you do is you take the tensor algebra of the endomorphism ring here. So here we will do similar. We will define in a similar manner. So I mean, this is also a vector space, of course. So you forget the ring structure. You see it as a vector space, and you take the tensor algebra, and then define some relations, quotient by some ideas. I will not define. So this is the Clifford algebra of my involution. It is a semi-simple algebra over F, and the center, again, the center is an entire quadratic extension, quadratic F algebra. So I have two options. Either K is a field, this means a quadratic extension of F. In this case, the Clifford algebra is central simple algebra over K, and otherwise K is S times F. And in this case, Clifford algebra is product of two central simple algebras over F. And we have also knowledge on the degree of this algebra, but we will not need for today talk, so I will not give.
I think in the same way as I was reminded before that the quadratic form should be of even dimension, I should ask that the degree. Here you.
Yes, even degree.
You said this, yes. But
Yeah.
Yeah, can you say that again?
Yeah. Yes, degree is even. And okay, so again, at a quadratic extension in both cases, this is just even again by zero element, and the discriminant of the involution is the square class of it. Okay. A very quick, small example, maybe. So, consider the quaternion algebra, AB, and then the involution. Okay, let's ij be the basis, and consider the inner homomorphism given by I, and then this unique simplex involution that I define. So the Clifford algebra of sigma is the quadratic extension given by this I, and the discriminant of sigma is the square class of A. Okay. So now we are, we have our invariance, so we can, I can give the classification result, but I will give in a different terminology. So first, let me make this remark. So whenever we want to determine given two objects are the same, whatever the same has the meaning, it is usually possible to translate this problem into the difference being trivial, whatever difference would means and whatever trivial would means. And in this case also, all the definition are possible, so the setup is there. So I will give in the second terminology, and trivial here will means hyperbolic. So I will need to define hyperbolicity for involutions, and that is, then I can give the result. So, algebra with involution, and sigma is isotropic if there exists a non-zero element such that sigma a equal to 0 and anisotropic otherwise. And sigma is hyperbolic if there exists an eigenvalence element, so this equal E, such that sigma E is equal to 1 minus E.
I think you want to say there exists an A in A without 0.
Oh, yes. Yeah, I have any syntactical algebra, yes. Thank you. Yes. And yes, for example, a very quick example on the quaternion algebra that's already here. So I took the from E5, right? So like if we assume take a quaternion algebra, but where A is a square, is 0 in F, and take this involution with I. That is not hard to see that this is isotropic. Basically, you have 0, 0, and this is not 0. Okay, maybe here I think. Okay, right. So now I can give the result. See, it's actually okay. Yes. And okay, another example without, I will not write, but in this split case that I refer as a split case. So whenever on the endomorphism ring, if we consider orthogonal involution on the endomorphism ring, so that it comes from a quadratic form. Whenever the quadratic form is isotropic or hyperbolic, then the involution is isotropic or hyperbolic, or vice versa. Right. Proposition. So we assume I equals 0, and using an algebra with orthogonal involution, anisotropic, if there exists a quadratic field extension such that over this field extension, my algebra splits and my involution is hyperbolic, then the degree of the algebra is at most 4. I will not give the proof of this. This is the technical part, but it is really handy computation. Next part, I would say. But I will use it to deduce the classification result. Yes. Sure. So I create 0 and let's any sigma f algebra, the f algebra with orthogonal involution. Yes?
No, it's fine. Sorry.
Involution. Such that. So degree is divisible by 4. index. Recall that index was defined. You write A as a matrix algebra over the division algebra, which is unique after isomorphism, and index is the degree of that underlying algebra. Index is at most 2, so this means that we are just considering matrix algebra over a quaternion algebra, basically. So you know the object. Index at most 2, and discriminant is trivial. Trivial. If you
did you say the indexes?
Yes, at the beginning I defined, but now I recall because it's quite some time. Right? Yes, exactly. So here you see, like the discriminant was, this basically discriminant is this center, right? So the discriminant trivial is if and only if the Clifford algebra is product of two central simple algebras. So by my assumption, the Clifford algebra looks like this. Central simple algebras over F. So if degree of A is strictly bigger than 4 and index of the simple component is at most 2, then sigma is surjective. And if one of the simple components, C plus or C minus, is 3, then sigma is hyperbolic. Okay. They are not good, definitely. I remember they were better. When I was here, they were better too. Okay.
This is the box with the bad ones.
Yes, indeed. I was trying many of them, but it seems just the quality is bad. So. Okay. So. Okay, the first item we do. Okay, the Clifford algebra I defined, and I gave already some information on it, but we know quite well the structure of the Clifford algebra. For example, this information, degree being divisible by 4, tells me that I have the following relation between the algebra and the component of the simple component of the Clifford algebra. Basically, this means that if I take tensor product of all, that thing split. But remember that the index of all these three algebra is at most 2. So basically, I have 3 quaternion algebra, and the tensor product of them split. This is okay, maybe not trivial, but definitely not hard. Using this fact, I can see that there exists a quadratic field extension. Quadratic field extension that splits all 3 algebra. Split. So very vaguely, I will. Those who are familiar with quadratic forms, they can see this as follows. So you have 3 quaternion algebra. You can take 2 of them in one side and 1 of them in other side. 1 quaternion algebra and 2 quaternion algebra instead of them, you can just consider 4-dimensional and 6-dimensional quadratic forms. But 6-dimensional quadratic forms that it obtains as the difference of two norm form of the quaternion algebra, and 6 is bigger than 4, so that will be isotropic. And so this means that the norm, the 3-dimensional part of the norm forms of the two quaternion algebra, you can choose one coefficient the same in both of them. But the norm of quaternion algebra and the quaternion algebra are really well related. That is, a coefficient, if I choose one coefficient the same, this means that a quaternion algebra has one quadratic subfield the same. And then I extend scala to this quadratic extension. I split that to quaternion algebra. But on the other hand, I had just the same things. So splitting two of them, then automatically I split also the 3. So all 3 is split. It's bad, but it's not trivial, but it's not hard. I was trying to just convince. Okay, so my algebra split, that means I am in the split case. So over K, my involution is basically a morphism of some vector space over K, and my involution is given by some quadratic form over K. Form over K. And as I said, we define these invariants in the way that in the split case they coincide with those for quadratic forms. So the discriminant of this quadratic form is the discriminant of the involution. This involution has involution sigma k, which is trivial. It was trivial already by the assumption, so when you extend, it remains trivial, of course. The same is that. And then the Clifford algebra, now the Clifford algebra, is the Clifford algebra of the involution, hence it is C plus C minus but over K, and these are also split. So I have a quadratic form over K, and it has even dimension and trivial discriminant and split. So trivial Clifford algebra. One last thing to say, I3 equals 0, this property, this is the assumption we have. It's not trivial, but with some work, one can see I3 equals 0 is preserved under quadratic field extension. So I3 K also is 0. Sorry. And so I have over K a quadratic form with trivial invariance, and K satisfy this property. So the result that I gave at the beginning, due to Elman-Lam, implies that this form must be hyperbolic. Elman-Lam 74 phi isotropic hyperbolic. Hyperbolic. Because hyperbolic forms, remember, they have the same, they have the trivial invariance. And this quadratic form hyperbolic, then the involution, adjoint involution is hyperbolic, but this is how I get my involution over K. So this means that my involution is hyperbolic. Now we look at the first proposition. So basically I form the quadratic extension over which my algebra split and my involution becomes hyperbolic. And so if I assume that degree is strictly bigger than 4, then the involution, the initial original involution cannot be so it's like sigma is hyperbolic. This is the conclusion. Okay. So for this was the first item. The second item, I will just say it by words. So basically, the idea is to repeat the first item until I get nothing. And I look at algebra. Degree, if degree is bigger than 4, then I apply the first item. I found isotropy, and I am able to split off the isotropy. That small part I can split off, but the process is nicely done, so that the involution that I obtain has the same invariance as the initial. So if I split, of course, I will remain with something smaller, so degree gets smaller, but the invariant remains remains trivial. So I am able to repeat the process. So I apply 1 until I reach degree 4, something that has degree 4. But yes, independent of the field, this property here, for degree 4 algebra with orthogonal involution, if it has trivial invariance, it's well known and not hard to see that this is isotropic as well. So basically, what I see, I repeatedly get isotropy, and this means that I am actually hyperbolic. And this, yes, put the second item. And yes, finally, and yes, like this is this second item here is the classification result for orthogonal involution. It corresponds to classification result for orthogonal involution, but for just these algebras, okay, I say quadratic pair, I will at least define. So let me quickly define. Quadratic pairs. Central simple algebra over F. Take a central simple algebra over F. A quadratic pair on A is a pair CF, where sigma is an involution. This you know, involution, and F is an F-linear map defined on the symmetric elements. F-linear map, and this should satisfy the following properties. So the dimension of the symmetric elements, okay, that's the degree of A, the n. So the dimension of the symmetric elements, this vector space, the dimension must be n times n plus 1, quotient 1, n, and the reduced map, reduced trace of any skew symmetric element. And this is like element x in your algebra, such that sigma x is equal to minus x. Reduced trace must be 0. And the second item, like for, okay, the map is defined on the symmetric elements, and for those elements which have the following form, like this, x plus sigma x, f is predefined. That is reduced trace of x. Okay, so I don't have too much time, so I will not write any more thing, and unfortunately cannot give an example. I was planning to give an example also, but just let me remark. So in characteristic not 2, as I said, the dimension of this vector space exactly what's determines whether the evolution is orthogonal or symplectic. So this exactly tells me that if in characteristic not 2, the evolution is orthogonal, and then in characteristic not 2 that I can divide things by 2 allows me to see that f is given just by half of the reduced trace. So in characteristic not 2, you have one possible F-linear map. It is half of the reduced trace, and then the evolution is orthogonal. So the concept is the same as I was saying. And in characteristic 2, instead, this condition tells you that the evolution is symplectic, and it can be many different non-isomorphic F-linear maps. So basically, this is the generalization modification that's needed to take care of characteristic 2. And this is exactly what corresponds in the split case, quadratic forms. And then, yes, this is the main result. So basically, for quadratic pair, for the quadratic pair, we have this classification result here. And the idea is really actually the same, but just with careful computation and some small modification. We were able to carry on. And the last thing is that, okay, I gave the explanation for index 2, but actually for index 4, also I can, recently I realized that we have the classification result also when the algebra has index 4. So index 4, and then you have trivial discriminant, and Clifford, one of the components is trivial. That implies quadratic pair hyperbolic. So yes, that is all what I wanted to say. We can proceed with questions. Thank you.